Okay, awesome. Okay, so thank you all so much for having me.
Actually, would it be all right if I introduced you first?
Yes, that works.
Yeah, so before I get to that, I want to just remind everyone to please hold your questions until the end, unless it is a really vital clarification question, in which case you can put it into the chat and I will read it to the speaker. But other than that, so today's speaker is Diana Powell. Diana is a graduate student at UC Santa Cruz, and she studies protoplanetary disks, planet formation, and exoplanet atmospheres. And she's going to be telling us about a wide range of the work that she's been doing. So, all right, Diana, the floor is yours.
Awesome, thank you, Camber. So yeah, I'm Diana Powell, and I'm a grad student at UC Santa Cruz. And today I'm really excited to talk with you all about protoplanetary disks and substellar atmospheres. And really in particular, I'll be focusing on the insights that we can gain from understanding each of these different objects from the perspective of microphysics. And so for the purposes of this talk, microphysics refers to the physics that governs the evolution of small particles in the presence of gas. And so the key question behind all of my research is, what is the origin, evolution, and nature of planets? And to address this question, I characterize planets in the planetary material and protoplanetary disks. And in particular, I use theoretical microphysical tools to peer beneath the veil of each of these stages of planet formation and to uncover the fundamental properties of both disks and atmospheres. So I will just briefly talk through the picture of planet formation that has emerged, which looks more or less like this. So we think that planets form in protoplanetary disks, either from the accretion of solids and gas or the gravitational collapse of material. So these protoplanetary disks really constitute the building blocks of planetary systems. Then once the bulk of the disk dissipates, a young planetary system remains, and the gas giant planets, if they're present, will be initially relatively hot. So the second stage is not usually included in diagrams like this, but I'm doing so because it represents a distinct observational stage with unique signatures and observing strategies. And then as time progresses, the planetary system will evolve. Many of the gas giant planets, if they're present, will cool. Planets will find relatively stable orbits, and the planetary atmospheres will evolve. Okay, so this is the general picture. But what we all really want to know is what I really want to know is how can we relate these disparate evolutionary stages to learn more about the formation, evolution, and nature of the full complement of planetary systems. And we're all really lucky to be alive at a time where each of these stages of planetary evolution is undergoing an observational revolution. And we have unprecedented observations of each of these evolutionary stages. So we can observe protoplanetary disks, such as the disks observed in high resolution shown here. And as a bonus, we can also observe protoplanetary disks undergoing active planet formation, like the PDS-70 system shown here, where you can see 2 points that are thought to be giant planets undergoing accretion. We can also observe young planetary systems directly, like the Beta-Pic system shown in the bottom left. And finally, we now have observations of over 4,000 evolved exoplanets. And so with all of this data, I think that this is really the era to start actively connecting planet formation to planetary characterization. And in particular, a promising avenue forward is to connect the properties of protoplanetary disks to the properties of exoplanet atmospheres. So when we look at observations of protoplanetary disks, we're looking at small dust grains and some different trace gas species. These recent observations are really spectacularly angularly resolved, but they're often limited due to a lack of probes of the primary disk properties, such as the total mass in the system and the detailed properties of the solid and gaseous mass constituents, particularly in the planet-forming regions of the disk. And then when we look at detailed observations of young and evolved planetary systems, we're often looking at their atmospheres. And similarly, these observations are often hindered by opacity sources, such as clouds and hazes that obscure planetary properties. And so to make the connection between disks and atmospheres, we need better physical models to interpret current and upcoming observations. And I'll argue in this talk that microphysics will be important in making this connection, and it might well be key to understanding the origin, evolution, and nature of planets. Okay, so in this talk, I'll start by talking about substellar atmospheres with a focus on clouds. And then I'll move on to discussing protoplanetary disks and the total amount of mass present in these systems. And finally, I'll bring these two topics together through a discussion of the evolution of carbon monoxide in protoplanetary disks. So let's talk about clouds. So we all have some intuition about clouds from our familiarity with clouds on Earth. But clouds are important beyond Earth and are in fact the dominant opacity source in most planetary atmospheres. Clouds are important tracers of atmospheric physics, such as mixing and transport. Clouds regulate the planetary climate through regulating radiative transfer and chemistry. And clouds really must be understood when determining precise atmospheric abundances. Also, often the clouds in an atmosphere are the only thing that we can see. So it's really an absolute necessity that we understand clouds when we're interpreting planetary atmospheres. And clouds appear to be abundant in substellar atmospheres. So here on the left, I'm showing a collection of transmission spectra of 10 different hot Jupiters, where many of these atmospheres have damped spectral features and this flattened or sloped optical spectra. And all of this is indicative of some optically thick absorber of stellar photons like clouds. Clouds may also have been observed directly in the atmospheres of brown dwarfs, which have atmospheric properties similar to giant planets. So in the middle here, I'm showing emission spectra of 2 brown dwarfs, and both of these objects have this broad absorption feature in the infrared that's not quite captured by the models here, and that's thought to be caused by silicate clouds in their atmospheres. And then clouds are also thought to contribute to observed spectral variability. So on the right here, I'm showing emission spectra of the same brown dwarf at 2 different times, where you can see that the amplitude of the spectra can vary significantly. So we know that clouds often dramatically impact observations of substellar atmospheres. And to me, this presents an exciting opportunity. So with an understanding of clouds, we can explain current observations, we can probe fundamental planetary properties, and we can predict future observational signatures. So let's start by understanding clouds. Oh, also, if there's a little bit of noise in the background, someone's fixing my heater today, but let me know if it becomes a problem. Okay, so there are 3 key microphysical processes of cloud formation. And all of these processes depend on the atmospheric conditions as well as other key properties. So the first process is nucleation, which occurs when a supersaturated background gas nucleates onto a seed particle. And there can also be homogeneous nucleation, where a gas nucleates without the presence of a seed. And then whether a species nucleates homogenously, heterogeneously, or not at all depends on the species-specific material properties. Then condensational growth occurs when a condensable molecule diffuses along a path and interacts with a cloud particle, and condensational growth occurs. And in my simulations, this process is often limited by gas diffusion. And then clouds can also grow via coagulation, where 2 particles collide, forming either a larger spherical particle or an aggregate. And this process is often limited in our simulations by particle number density. And so I approach the study of clouds using these microphysical processes with the community and aerosol and radiation model for atmospheres known as CARMA. And so some of you may be familiar with CARMA because it's a well-tested code that has been applied to nearly every planetary body in our solar system with an appreciable atmosphere. So CARMA works on this Eulerian grid of particle size and altitude, where particles can grow and move into larger bins and then evaporate and move to smaller bins. And then particles can also move vertically along this grid. And CARMA turns out to be a really particularly powerful tool because it calculates the fully resolved cloud particle size distributions, which is crucial in shaping the spectra, from first principles in a time-dependent framework. And so on the right here is a general picture of how CARMA operates. So here I'm showing altitude in the atmosphere as well as temperature and pressure. So the condensable gases are mixed upwards from a reservoir in the deep atmosphere until they reach a point where the gases become supersaturated and cloud particles form via these microphysical processes. Then once they're cloud particles, they can themselves be vertically mixed or settle gravitationally. And so here's a quick primer of some of the results that I calculate with CARMA. So I'm plotting the mass density of condensed cloud particles as a function of particle size and atmospheric pressure. And here, each of the different colors indicates a different cloud species. So as you can see, each cloud species forms at different times and has different particle sizes and different vertical extents in the atmosphere. And then our results also tend to reach the steady state, as there's some variability, which may be real, like the climate cycles that we have on Earth or also on Venus. But for the remainder of this talk, I'll be showing time average solutions. And so with these results, we can now answer key questions such as the impact of the cloud particle size distribution on observed spectra. So on the top right here in black, I'm showing a model transmission spectra for a hot Jupiter with our fully resolved cloud particle size distribution. And then on the same plot in blue, I'm showing the transmission spectra if we take an average cloud particle size for each cloud species and conserve the total cloud mass. So as you can see here, both the amplitude and shape of the transmission spectra changes between the two cases. And this is particularly dramatic in the optical and near the broad cloud absorption features in the infrared. And so this indicates that understanding the cloud particle size distribution is important when interpreting observed spectra. And then because this framework also considers barriers to cloud formation, we can also predict which cloud species dominates the observed spectra. So in the bottom right here in black, I'm showing a different model transmission spectra for a hot Jupiter where we include the opacity from all of the cloud species that form. And then in gray, I'm showing what a cloud-free transmission spectra would look like. And then in the different colors, I'm showing what the spectra would look like if we only include the opacity from a particular cloud species. And you can already see in gray to black here that clouds make a huge impact. But in this case, it's the silicate clouds that dominate the cloud opacity across this really broad wavelength range. And in addition to impacting spectra, clouds may also serve as probes of planetary properties, such as their interior thermal structure. So here I'm showing emission opacities as a function of wavelength and atmospheric pressure for a planet that has the same upper atmosphere thermal structure, but different internal thermal structures. And here the dotted white line indicates where the clouds become opaque. So for the high entropy planet on the left, with a hotter interior, clouds are opaque as high in the atmosphere as 0.1 bar. But for a planet with a lower entropy interior, clouds only become opaque at around 10 bar, so much deeper in the atmosphere. So statistically, clouds may thus be able to serve, when we have a larger sample size, clouds may thus be able to serve as probes of planetary interiors as they are sensitive to planetary properties across different scales. And with this framework for microphysical clouds, we can directly calculate the timescale of each cloud formation process, which is interesting. So we can look at how the timescale of cloud formation interplays with other things like atmospheric large-scale motions. So there's a lot of information in this plot, but right now I want to draw your attention to the evaporation timescale in particular, and notice that evaporation is very fast when thermodynamically favorable. And with this in mind, now let's talk about predictions for future observational signatures. And in particular, I want to discuss the case of inhomogeneous clouds on hot Jupiters. So hot Jupiters are likely tidally locked, such that they have permanent day sides, this extreme insolation gradient, so permanent day sides, permanent night sides. And this insolation gradient drives a super-rotating equatorial jet that operates to reduce the gradient, but it does so less efficiently at hotter temperatures where re-radiation dominates. So these planets thus tend to have very hot day sides, a hot eastern limb, relatively cool night sides, and a cool western limb. And really the atmospheric inhomogeneities on these planets, as well as their high temperatures that cross many different condensation curves, make them exciting laboratories for understanding cloud physics, because we think that many species should form and they should do so differently in different areas of the planet. And so let's consider the case where the day side is too hot to form clouds. And because we know that evaporation is fast, there should be no direct transport between the cooler west limb and the hotter east limb if the dominant atmospheric flow is along the equatorial jet. So in this case, we would expect from equilibrium thermodynamic arguments that the clouds on each limb would have different compositions and form at different heights in the atmosphere. And that's what we're showing here on the right, where I'm plotting pressure temperature profiles on the cooler west limb and the hotter east limb for the same hot Jupiter. But what do we find about the clouds when we use microphysics? So here I'm showing cloud particle mass densities as a function of particle radius and atmospheric pressure, where each color again represents a different cloud species. And so on the hotter east limb, clouds form higher in the atmosphere and grow to relatively small sizes. On the cooler west limb, more cloud species form, they do so deeper in the atmosphere, and they grow to relatively large sizes. And then the polar regions represent an intermediate between these two. So if we compare these results to expectations from equilibrium modeling, we find that several species that we expected would form are not actually able to abundantly form given these atmospheric conditions. So if we translate these cloud properties into transmission spectra, we predict that there should be a significant difference in both amplitude and shape between the east and west limbs of the same hot Jupiter. So in black, I'm showing the calculated transmission spectra on the east and west limbs. And gray here, I'm showing what the east limb transmission spectra would look like if there were no clouds. And then in blue, I'm showing the opacity continuum due to clouds. So on the west limb, cloud opacity is significant across a broad wavelength range where it flattens the observed transmission spectra. But on the east limb, clouds contribute to this muted and sloped optical spectra, as well as this broad absorption feature in the infrared due to both silicate and aluminum clouds in this case. And then there's also this intriguing clear window around 3 to 10 microns that could allow us to peer through the clouds. And this difference in transmission spectra corresponds to an observable difference in limb radii as viewed in transition. So here I'm showing 2 scale limb radii differences, so the 2 different limbs of the planet, in the case of clouds on the top and a cloud-free atmosphere on the bottom. So the cloudy atmosphere has these distinctly asymmetrical limb radii that are significantly more inhomogeneous than the clear atmosphere case, which also has some limb asymmetry, but that's just due to temperature differences alone. And so if we try to fit a transit of this inhomogeneous atmosphere using a homogeneous atmosphere model, we end up with residuals as shown here on the left. And to first order, these residuals look like what we'd expect to see if the transit timing was not known well enough. However, these residuals are chromatic and change with wavelength in a way that's characteristic of the presence of clouds. And we've shown that with James Webb, we should be able to robustly detect atmospheric inhomogeneity due to clouds with observations of just 2 transits. So here on the right, I'm showing how asymmetrical an atmosphere appears to be as a function of equilibrium temperature for both the cloudy and clear atmosphere cases. And then how well we can detect this asymmetry is shown in blue, where darker blue is a better detection. So the hotter planets in our sample have a significant detection of atmosphere asymmetry that is always stronger in the cloudy case and can be robustly detected with James Webb. And I'm also working on interpreting observations of exoplanets in emitted light, reflected light, and using transmission. I'm using this new 2-dimensional model of microphysical clouds, where I calculate how cloud properties change as clouds are vected along the superrotating equatorial jet of a hot Jupiter. And so here I'm showing condensed cloud mass of different species as a function of planetary longitude and pressure. And using these models, we can robustly determine the impact of clouds on high resolution observations and exoplanet phase curves. So more on this soon. And then I'm not really going to talk about this in detail, but I just want to quickly point out that we've applied this modeling to very low gravity brown dwarfs, which have atmospheric properties similar to planets, but much more data. And so here I'm showing the color magnitude diagram for brown dwarfs with this very low gravity sequence of brown dwarfs highlighted in yellow. So relatively newly discovered sequence. And so if we were to model these very low gravity profiles with clear atmospheres, they would lie in this region of the diagram where we do not really observe any brown dwarfs. But if we model clouds in these atmospheres using microphysics, then the same points lie here, well, without microphysics, so just equilibrium condensation models. And here they're much redder, although they start to become more clear at lower equilibrium temperatures. And then when we instead consider microphysical clouds, those same points lie here. And we can see a distinct shift towards the red region of the diagram, which is particularly dramatic for cooler objects. And that's something that's particularly encouraging about the microphysical results here, so that they follow the straight slope of the sequence down to the reddest regions where we're currently discovering objects instead of curving off to the blue. And so these results demonstrate that bin scheme resolving the size distribution of clouds, can really naturally reproduce this very low gravity sequence of brown dwarfs. Okay. So we've discussed the importance of understanding clouds in substellar atmospheres, which is important in constraining evolved planets. And now let's turn our attention to protoplanetary disks, which are the locations of planet formation. And I'll start by talking about the interesting question of how much total mass is present in these systems. So the most common tracers of protoplanetary disk properties are dust or trace gases such as CO gas, as these are relatively easy to observe. But due to a lack of direct probes of the main mass constituent, H2, previous measures of disk mass have relied on some tracer to H2 ratio. But we know that processes such as grain growth and drift should alter the dust to gas ratio from the typically assumed interstellar medium value. And several lines of evidence also suggest that gas phase CO, so particularly in the commonly observed upper disk layers, is also depleted in disks. And so this begs the question, or the questions, how can we measure the total disk mass without an assumed tracer to H2 ratio? And also, what is happening to all of the CO? And really getting to the bottom of these questions is of the utmost importance for understanding disk physics, since both dust and gas are used to trace a broad range of disk properties. Okay, and we can begin addressing these questions by considering multi-wavelength observations of disks in the millimeter. So here I'm showing a visualization of observations put together by Sean Andrews of the disk TW Hydra. So here the disk appears smaller in radius, so the same disk, different wavelengths, and the disk appears smaller in radius at longer wavelengths. And to introduce some terminology, I refer to the maximum radius in which there's emission at a particular wavelength as a dust line. And as others have suggested, these observations may be signatures of particle drift. And I'll take a step back for a moment to talk about the two main processes that can limit particle growth in disks. And here I'm showcasing work done by my undergraduate student, Elizabeth Yunnerman, who has just been accepted to graduate programs that will be starting this coming fall. So in the shaded regions of phase space that I'm showing here, particles are unlikely to reside due to barriers to their continued growth. And so the process that's the most relevant in the inner disk is fragmentation, which depends sensitively on the assumed particle material properties. So fragmentation may be really significant for a range of particle sizes throughout the disk, or may only be relevant for a narrow range of particles in only the innermost disk regions. Then in the outer disk, particle growth is often limited by drift. And as I'm interested in the dust lines in the outer disk, let's talk about drift in more detail. So particles drift in disks because the gas feels an outward pressure gradient that causes particles to feel a drag that removes some of their angular momentum and causes them to drift inwards towards their host star. And so I'll take a little bit of time walking through this timescale since it will lead to the key equation for this portion of the talk. So the drift timescale of a particle is given by the orbital distance, its orbital distance r, divided by the velocity difference between the gas velocity and the Keplerian velocity. And then there's the stopping time parameter tau s, and that's because the particles are neither quite at the gas speed nor at the Keplerian speed. And so we observe small particles that are relatively well coupled with stopping times less than 1. And in this regime, as particles grow larger and the stopping time gets larger, they will also drift faster. And we can write the stopping times in terms of standard disk parameters and then rewrite the drift timescale. So this timescale is exactly the same as what I've written above and is just rewritten in terms of the total gaseous surface density. And you can understand why this depends on the gas surface density, because if you have more gas, then you'll also have more gas drag, and that will change the stopping time for a fixed particle size. Okay. And if we rearrange this equation like this, we see that we can derive the total disk surface density as a function of radius if we know the rest of these quantities. So in particular, if we know the maximum radius in which particles of a given size are present. And just notice here for a fixed particle size and fixed radius, a larger surface density means that you have a longer drift timescale because you're better coupled to the gas. Okay, so thus, if we have some a priori knowledge of the particle drift timescale, we can use this method to derive the total disk mass. And to motivate my choice for drift timescale, here I'm showing a dust evolution simulation using models by Till Bernstein that shows the surface density in solids as a function of particle size and radius in the disk. And in particular, I want you to focus on the dashed red line here that indicates the maximum size that a particle can grow to before it drifts inwards. And so as you can see, in the outer disk at late times, particle growth is limited by drift and collisional destruction becomes less important. And out here, the maximum, so when you're drift limited, the maximum particle size at a given radius is set by particles whose growth timescale is equal to their drift timescale. But then if you look at a particular distance, the particle size is reduced over time as larger particles drift inwards. So we can therefore expect that the largest particle size at a given radius, at a given time, will be the particle size with growth and drift timescales equal to the current age of the system. So these particles have had the entire age of the system to grow up to the maximum size at a given time at a location before they drift inwards. Okay, and we won't use this right now, but I want to draw your attention to the fact that the dust to gas ratio is also decreasing with time, and we'll come back to that later. But so with this, we can now assume that the drift timescale is comparable to the age of the system. And so now we can determine the surface density at a given radius if we know the maximum particle size at that location. So we can infer the particle size if the observed wavelength corresponds to the primary particle size contributing to the observed emission at the disk outer edge. And we can measure the disk size to determine the radius in which these particles are the maximally sized grains. And so this method allows us to derive the disk surface density without assuming a tracer to H2 ratio. And that's because we only care about how fast the particles drift, which depends on their size, and not on how many particles are present. And so here on the right is a quick visual summary of this new picture of protoplanetary disks. So large particles of size S1 are present throughout the disk until they reach a radius where their drift timescale is equal to their growth timescale, which is equal to the age of the system. And if you look at a disk at this disk with an observing wavelength approximately equal to S1, then you will see a disk with this radial extent. And then the same is true for smaller particles of size S2 that extend throughout the disk until they reach a radius where their timescales are equal. And again, for even smaller particles of size S3, where if you were to look at this disk at a shorter wavelength comparable to size S3, you'd see a much more radially extended system. And so we've applied this model to 7 protoplanetary disks with previous millimeter observations that show decreasing disk radial extent with wavelength. And here I'm showing some of these observations for 3 out of the 7 disks in our sample. And as a bit of a technical aside, this is how we're actually measuring the disk outer edge, which is an important measurement as it's one of the fundamental quantities in our modeling. So that's the maximum radius in which particles of a given size are present. So we developed an MCMC method for finding the disk outer edge through modeling the disk interferometric visibilities using a nuclear profile. So on the left here, I'm showing a sample set of modeled visibilities. And on the right, I'm showing a model surface brightness profile. So here, ignore the red line and see in blue that our method for finding the true disk outer edge is robust, even if there's brightness dips caused by substructure. Okay. So here I'm showing the total gaseous surface densities for the disks in our sample. So the black points are the surface densities derived from dust lines, and the red or blue lines are previously published surface density profiles derived either from CO emission or combined multi-wavelength observations of dust. And what I've done here is just renormalize these previous profiles so as to match the dust line derived surface densities. And you can imagine that if we had many more points from dust lines, we could just directly fit the profile shapes, as I've shown here in the bottom right in the dashed line for DAR25. But right now we can match previous profiles quite well, and notice that these profiles do not all have the same slopes, and the dust line derived points are not all straight lines, and instead follow the curves of these profiles. And so this really did not have to be the case. So for example, FT tau and TW hydra have different profile shapes, but for both the dust line points match the previously published profiles. And remember, we showed that substructure does not affect these results. Except I'll tell you that there's one exception to this, and that's if you have some prominent substructure like a ring that is the very outermost thing in the disk. And then if we had some prominent substructure that was trapping particles, what would we expect in that case? Well, we'd expect that all the different sizes would end up at the same location. So we can look and see if there's a disk in our sample that looks like this. And I'll spoil it by saying it's AS209 in the bottom left, where here the furthest out point does not match the previously published profile. So you see this data point floating by itself. But if you look, there's 2 points there representing different particle sizes that are at the same location. And so that's exactly what's going on here. So there's a ring that's the outermost region of this disk. So if there's substructure, it won't just give you random sizes at random radii. They'll be at the same radius, which will be the ring location. And so if there's not one outermost ring, you'll get a bunch. So if there's one outermost ring, you'll get a bunch of sizes at the same radius. And otherwise, as we've shown before, our results will not depend on substructure. So all of this is what makes me encouraged that this model is doing well. And so we can now place these dust line derived masses in context. So here on the left, I'm showing total gaseous surface densities in black compared to previous tracer derived surface densities and the minimum mass solar nebula. So the disks in our sample tend to be 9 to 27% of their host stellar masses. So significantly more massive than the minimum mass solar nebula. So that's about 2%. And then for the 3 disks in our sample with resolved CO emission, our estimates are 3, 40, and 115 times more massive than previously published, indicating that CO depletion is not uniform across different disks. So these results indicate that dust is a more robust tracer of total mass because we uncover a reduced gas to dust ratio that is roughly consistent across our sample, while the CO to H2 ratio varies more strongly. And I'll come back to this later in the talk. So here I'm plotting the tumor Q stability parameter as a function of radius in the outer disk for the disks in our sample, where a tumor Q parameter less than about 1 is where you would start gravitationally collapsing under your own self-gravity. So all of the disks in our sample are stable to gravitational collapse, except for one disk which approaches the limit of tumor Q stability. And actually that disk does show some subtle signatures of what might be gravitational instability in its morphology. But note that all the disks in our sample have low Q values at certain radii. And so we think that when you form disks, they are accreting because they're marginally unstable. This marginal instability might be helping to raise spiral arms that throws material onto the star efficiently. And we still think that all of this is going on. But after this early phase of star formation, you really need MRI or disk winds to kick in to drive accretion. And it's really a big mystery how disks are able to accrete efficiently at late times. But maybe if some disks are actually close to gravitational instability at these later times, you do not need a lot of these accretion processes to be happening because at least some disks, particularly these bright massive disks, seem to maintain much of their mass. And so in our modeling thus far, it has not been required to know an expected dust surface density. So we don't need to know the dust surface density. But given our results, we can now use models of coagulation to compute the dust surface densities, since we know, so we can basically leverage the growth timescale in models of coagulation, because we know that the maximally sized particle at a given location has a growth timescale equal to the age of the system. And so here on the right, I'm showing surface densities for the disk FT tau, where the blue line is the total gaseous surface density derived using my dust line method. And then the solid black line is the observed dust surface density. And then here, the dashed lines are dust surface densities derived using analytic and numerical treatments of particle coagulation. And so for the disks in our sample, we derived depleted dust to gas ratios of around 10 to the minus 3 in the outer disk, which is a common outcome of models of grain growth and drift. And so in these models, where did the dust go? And it went into the inner disk, but you can also imagine it being incorporated into planets. And it is worth noting that in these models, the disks formed with an initial dust mass that is a factor of 10 greater than is presently observed. Also, being able to constrain the dust and gaseous surface densities using this method can allow us to empirically constrain the dust opacity, which is particularly exciting because the dust opacity remains one of the largest sources of uncertainty in studies of protoplanetary disks. Okay, so here's this new picture of disks where they may be more massive than previously appreciated. So the total dust mass is the same, but the total gas mass is an order of magnitude larger. And these qualitative changes to models of protoplanetary disks will have significant implications for theories of planet formation, particularly for any process where the amount of gas affects the evolution of solids. So that could be affected by this picture. And I also want to emphasize that our model indicates that there is more dust mass at early times, which helps bring agreement between the discrepancy in disk dust masses and the mass of extrasolar systems. Okay, so we've discussed the total mass in disks, but what is happening to all of the CO gas in these systems? And we really want to know the answer to this question because CO has been used as a tracer for a broad range of fundamental disk properties. And to answer this question, I will combine the two methods that I've used so far in this talk. So modeling clouds and modeling disks. And I'll start by saying that it's not just my modeling that indicates that CO is depleted in disks, so not by any means. So on the left here, I'm showing the CO abundance in the disk TW Hydra as a function of radius as compared to the abundance that we would expect from observations of the interstellar medium. That's work done by Camber here. So you can see that the CO gas appears to be significantly depleted. And then the same is true if we look at large samples of disks. So here I'm showing an ALMA survey of disks in Lupus, where the disks span several orders of magnitude in dust mass on the top, but have fairly constant gas masses estimated from CO. So in short, we observe much less CO in disks than we would expect, or that would be predicted using previous disk models. And so to address this problem, I've coupled my model for protoplanetary disk properties with an adapted version of the models that I use to study cloud formation and planetary atmospheres. And in this context, I'm modeling the formation of ice on dust in disks. And in particular, the nucleation and growth processes in the ice formation scheme that I use include the Kelvin effect. which quantifies the stability of ice particles through considering the strength of the molecular surface bonds. So I like to think about this effect in terms of geometry, where an ice molecule on the surface of a small grain will not be able to molecularly bond to as many neighbors as it would on a large particle. And so in short, the Kelvin effect causes large particles to nucleate and grow more easily. And the particle sizes are important here because they regulate the level of depletion of gaseous CO. So if we approximate the disk temperature structure as shown here on the left, so the vertical disk temperature structure, where the disk is roughly isothermal until it reaches a height where surface layer heating is efficient and the temperature increases. In the midplane, the disk will be cold enough for ice to form on dust grains. So there'll be a region of the disk where ice is stable, and then a region where evaporation or photodesorption could occur. So if the ice particles that form in the midplane are small, then they can be lofted to the upper regions and evaporate such that CO gas is not significantly depleted. On the other hand, if the ice particle is large, it can deplete the CO gas in the midplane. And so that's what I'm showing here on the right. So once the initial abundance of CO gas, shown in solid black, is depleted in the midplane, as shown in gray, there's a concentration gradient, which is smoothed by vertical diffusion over time. And this would ultimately lead to a depletion of CO in the observed upper levels, as shown in red, solid red. And so this is the so-called cold finger effect, which can lead to a large depletion of CO gas in the upper disk. But the particles and gas in the system evolve radially as well as vertically. So at early times, gas will be depleted fastest just exterior to the midplane CO ice line in the outer disk, where vertical gas diffusion is faster. Then with time, CO gas is increasingly depleted in the outer disk as diffusion has time to operate. And then in the inner disk interior to the ice line in the midplane, ice particles will drift inwards until they reach a warm enough region of the disk where they release their volatile content. And so this will cause there to be an increased abundance of CO gas in the inner disk that can then be accreted onto the host star. So let me quickly walk you through this potential evolution of CO in disks. So in the outer disk, CO gas is continually mixed down towards the midplane, where efficient ice formation occurs on large particles. These large particles drift inwards towards their host stars. And once these ice particles drift inwards to the hotter regions of the disk, they release their volatile CO back into the gas phase, and some interesting cycling of material occurs around the ice line. And then there will also now be an enhanced abundance of CO gas in the inner disk that can be accreted onto the host star over time. And so with this model, we find good agreement between our results and observations, as I'm showing in plots B through E, so the small plots around the big plot. And in our modeling, we find that this process depends strongly on diffusion, which contributes to the observed variance of CO depletion in different disks. So in the large plot here, you can see that the amount of observed depletion in the outer disk depends on the amount of diffusion that is operated in the lifetime of these disks. And I will note that this process is also applicable to other volatiles in disks. So really the microphysical processes of ice formation both regulates the observed abundances of CO gas and is crucial in determining the radial composition of protoplanetary disks. And with modeling like this, and with many more species with time, so with modeling like this, we can get a handle on the bulk diffusive properties of the system and the distribution of material in the solid and gas phase in the midplane that could be being formed into planets. Okay. So in conclusion, I've talked about understanding substellar atmospheres using cloud microphysics, and I've discussed uncovering fundamental properties of protoplanetary disks using particle aerodynamics and ice formation. I've shown that clouds are sensitive tracers of planetary properties, that clouds on the limbs of hot Jupiters are inhomogeneous and can be detected with James Webb, that resolving the size distribution of microphysical clouds helps to naturally explain the very low gravity sequence of brown dwarfs, that disks may be more massive than previously appreciated, and the microphysics of CO freeze-out and particle drift controls the observed abundance of CO gas. Thank you so much for having me.
Thank you so much, Diana. All right, if you have a question for the speaker, you can either use the raise hand feature, or you can put your question in the chat and then I will read it. And I see we have a question from Ninka.
Hi, Diana. This is Ninka. Very nice to meet you. Very interesting talk. I am a little confused though about your, well, I guess there are two things. Let me start with the first one. So when you're deriving your gas surface densities, you say that, and you show, I think, about 7 disks. you show that only for one case there was this ring dependence. The problem is that most of your disks have rings if we look at the high-res ALMA observations. So why don't we see it in any of the others? So like I quickly looked it up. FT tau, DOR 25, HT163296. All of those have rings, but yet you show they're following your curve. So I don't understand that.
Yes, absolutely. So with rings, we really need multi-wavelength imaging because you see a ring, but it's not really clear how effectively that's trapping particles of different sizes. So I guess I should back up and say for my modeling, all I care about is the furthest out radius that those particles are present. So if there's rings interior to that, it really doesn't matter in my modeling. At most, I mean, it really doesn't. I really only care about the maximum particle at a maximum radius. So in terms of if it's a ring interior to that point, we don't care. So for the other disks in my sample that have substructure, it's interior to the outer radius. And in every image that has the distinct substructure, it's in the inner disk, not the outer radius where I'm observing at that given wavelength. But in the case where it is the outer radius, like AS209, which I still model using this method, you can actually distinguish whether you're looking at the outer edge due to drift or the outer edge due to a pressure trap if you have multi-wavelength imaging. So that's what I'm showing here. So what we'd expect to happen basically is that particles of different sizes are feeling the pressure traps from the gas. So if the outer edge is set by drift really strongly, I mean, if the outer edge is set by a trap really strongly, like here, then in multi-wavelength imaging, you should expect that the larger particles are located in this narrow ring around, this narrow ring around the dust trap, and then smaller particles would be in a much broader ring. But then you could look interior to this point, and you should also then be able to pick out the edge set by drift, which would be further out for the smaller particles and closer in for the larger ones. And I think there's indications of this being seen now in the multi-wavelength imaging of some of these disks in high resolution. So there's ways to get around the substructure either way.
But so what you're saying is that regardless of the presence of pressure bumps, there is that outer radius is defined. That seems contradicting with the dust evolution work by Paula Pineda, who shows that dust disks just become very, very small over short amount of time. So maybe there's a difference here in the parameter space, but.
So I do really care about the very outermost region of the disk at different wavelengths. So it is a bit different than Paolo's work, although we could talk about it more in detail. I will say that there's one in Thomas Henning's group, and I'm kicking myself for not remembering the student's name, but he's been working with the same drift models that I have. So testing this dust line method and adding pressure traps into the interior regions of the disk. I haven't seen his updated results yet, but it wasn't as much as an order of magnitude difference before. So I don't think it would actually have a large effect.
I'll take a look at your paper for that detail. And if I can ask a second question about the CO chemistry, so kind of the second part that you showed. It's good to be reminded that all these lupus disks with low gas-dust ratios, they have been, so most of those disks have no substructure, at least not the very extreme kind like we see in like HT163296, etc. Most of those disks are unresolved and many even undetected. So it may be a little dangerous to extrapolate the results from, like, you're choosing bright disks, which I understand because we have the information there, but to extrapolate the results from the bright disk to all of those smaller lupus disks.
Absolutely. So the disks that I actually model in this way fully, these 4 disks around are certainly bright, large, and very well resolved. For one, I think Ion Loop is the one that I don't really like the mass estimates that I have externally. Well, actually, no, I should look back. But not all of these have been modeled with the dust line method. But they have other nice, robust mass estimates. So, but I agree. So I showed this here mostly because I want to get across that in both well-studied disks like TW Hydra, and then when we look at large surveys, it seems like CO depletion is pretty pervasive, just in the sense that it's something we need to address as a field. But I'm not going to take a stab at modeling those disks, certainly not using the methods that I have so far until they're very well resolved. Yeah.
Okay, thank you.
All right, we have a question in the chat from Munir Humayan, who has 2 related questions about CO. So the first is, for the CO observations, do these observations cover are the other carbon-bearing molecules to ensure that CO is not being converted into hydrocarbons or other carbon species, but is actually being depleted via condensation? And then also, is it known whether the CO is first converted into a more condensable species and then condensed?
Yeah, so those are great questions. I don't have super satisfying answers for you right now, but I'm thinking about this because if you look at our solar system, there's evidence that there's stuff like photochemistry happening in the CO that's formed in comets. So there's things that need to be worked out and considered. What my modeling shows is that you don't need to have a huge amount of chemistry happening to get CO depletion, but chemistry certainly does happen at some point in these disks. So where and how and how much is something that I think we need to work out more fully. But basically, we do now have observations of other species in these disks, so that's something that I'll be looking into in detail. But I don't have a great answer to either of your questions, and whether or not it would be converted to something more volatile than CO and then depleted. CO is if anything, incredibly volatile in these disks, so I don't think that would be necessary. Although if it does happen, you would expect that you would need less diffusion to get the same amount of depletion that we observe if it's being rapidly converted. Both of those I don't have a great answer to though, but I'm trying to think about different observational tests that we can use for this model.
All right, Steve.
Hi, this was a really fascinating talk, and I'm really glad I caught it. And it's nice to meet you. So first of all, I totally agree that disks are more massive. The minimum mass solar nebula was an absurdly low estimate for the amount of mass. And so in 2007, of course, we updated it using some of the constraints from the Nice model. And we found, yeah, at least 0.06 solar masses for our disk, probably higher. So I'm not surprised to see that, but I'm very intrigued by this idea of CO cycling in. I'm wondering if we can make a connection to something we published before. In 2015, in our Monga and Desch paper, we tried to explain the abundances of noble gases and basically hypervolatiles in Jupiter's atmosphere as being due to these gases being trapped in amorphous ice on dust grains, drifting inward and then releasing their volatiles. And we would have predicted that all of the species should have a factor 3 increase, and including oxygen, which Juno has just confirmed. So CO would fit into this, I suppose. Is there a way of estimating how much the CO to H2 ratio would be enhanced in the inner disk due to this cycling of dust from the outer disk?
Yeah, absolutely. So we do that in the paper, which I'm still working on the review report for. But yes, absolutely. You can look at this. That's the main product is the CO to H2 ratio throughout the disk.
Oh, super. Okay. I'm going to put a link to the Monga and Desch paper in here because I don't think enough people read it. But yeah, that's really great. There's this connection. Thank you very much.
Right. We have a question in the chat from Stanley Yin, who says, your results for increased gas mass do not seem to solve the problem from Manara et al. That there is not enough dust mass to form exoplanetary cores. So if you would like to comment on that.
Yeah, so that note is not that, our modeling implies that there's an order of magnitude more dust in the outer disk in all of these systems at early times. So it's the same amount of dust mass now, but if you go back like 500,000 years, then you get an order of magnitude more, and that helps resolve that Manara et al. Result.
All right, thank you for the clarification. Another question in the chat from Varden, who says, thanks for the nice talk. If the gas mass of the disk is actually an order of magnitude higher, then the planets that are possibly forming rings would migrate inwards much faster, and we will not observe them now. Can you comment on the disk mass problem from a perspective of planet migration?
Yeah, from the perspective of planet migration, well, so I'm not sure if I'm the most up to date on this literature now, but my understanding is that it's a difficult problem regardless of the disk being an order of magnitude more. I think it's something we'll have to figure out as a field as being an issue. I also think with these more massive disks, it's really, really easy to form, in certain cases, it can be really easy to form massive planets, and we might be forming an abundance of them. That might not actually be a problem though, because of planet-planet scattering and other planet formation things that can happen at late times. But basically, I think that is a good question that I don't have a great answer for.
All right, and then we have a question from Everett.
Really great talk. You went through a bunch of huge results. I'm just trying to catch up because they're really powerful, solving some big problems. I was wondering about the inhomogeneous clouds. If you could just explain a little more about why the morning and evening terminators are different, have different particle sizes, and if is it a 3D GCM you're putting in to kind of?
Yeah, so I'm working on coupling, on better and better couplings of 3D GCMs. That's what I'm doing here right now. So my cloud model that I use is a 1D model. It has been made 3D and incorporated into Earth climate models, but has been highly parameterized. And right now, in the version that is less parameterized that you can use for exoplanet atmospheres, you can't directly plug. Well, you can, but it's like a 1-to-1 with real time and computing time, so super slow. So I'm working on building that up with time. And so what I've done here to get these results is to look at, well, maybe I'll start, to look at a particular case where we think the day side's so hot that you can't transport clouds that way. But your east limb and your west limb, so even though your east limb's hot, you should form clouds. Your west limb, you'll form clouds. And so this is maybe the case that we'd expect to have the most dramatic and homogeneous atmosphere. And so what you end up getting is that on the east limb, you're barely supersaturating your clouds. You form these small particles. They form really high up in the atmosphere. They still contribute a lot to the spectra because they're so high, and small particles make interesting features. But so this is just really, you can barely supersaturate your gas. But then on your west limb, you get huge supersaturation. It happens deeper in the atmosphere. Clouds particles can grow basically up to the limit where they're then settling. So their particle size on the west limb is not limited by supply, but on the east limb it is. So that's one of the bigger differences between the two. And from this model, you can really see how clouds are super sensitive to planetary properties like temperature, and how when we're looking for features, it might be beneficial for us to look at particular regions of the planet where we can gain more information. So here, like the east limb versus the west. I hope that answered your question. Okay.
Yeah. So it's a growth. They have more time to grow, you're saying, is why they're so much bigger.
I guess I should say that maybe at the east limb, you get supply limited really quickly, so you can't grow bigger. On the west limb, you have enough gas around because you get this huge supersaturated range of gas to play with, that you can grow really large until you then start to experience so much gravity that you settle out.
Thank you.
All right. And then we have a question in the chat from Diane Wooden, who says, my question is about the porosity of growing particles. A primary supposition is that the max particle size is similar to the wavelength at which the outer disk radius is measured/modeled. Katuaka et al. 2014 show that the dust opacity extends to longer wavelengths if the particles are porous. How might your results change if porous particle opacities, tongue twister, were considered?
Great question. So I'm working on this right now, or briefly, off and on with Till, where we are seeing how much we can change particle properties and still see dust lines. So actually, we can constrain how aggregate these particles could be. So they have to have a filling factor of no more than like 0.5. Otherwise, you totally wash out signatures of dust lines, as you said. So you'll basically get a disk that's the same size at every wavelength, because porous particles start to act, I think in the Kataoka version, they act like the little small monomers. So you end up looking like small particles everywhere, and you get a disk size that doesn't decrease with wavelength. So you have a limit on how porous you can make a grain be. If we know porous optical properties well, there's a limit to how porous it can be before you smear out the signal, and we no longer expect to see dust lines.
All right. I actually have a question about your gravitational instability calculation.
Mm-hmm.
So most of these disks are gravitationally unstable at some radius based on the Tumori Q, right? But we don't really see like massive spirals in these systems. And so I was wondering like why you think that is, and in particular, what sort of temperature did you assume when you were calculating your Tumori Q parameter?
Yeah, so the temperature that I assume for this parameter, that's a good question, because the temperature comes in really, really minimally to other parts of my model, but more so here. So I assume that these disks are fully passively irradiated in the outer disk, and then use a very simplified model for how the temperature structure should look from there on out. So that's Eugene's work with Goldreich and Chiang, that paper. Yeah, so a flared disk, passive irradiation, we get a temperature structure. So that could change these results. So yeah, I guess I would say here Only one of them actually gets a Q that's slightly less than 1. That's DAR25. That one has rings, actually weirdly at the location. I don't know if you necessarily expect this, but it weirdly has rings right at the location where it looks gravitationally unstable in these models. I talked to some observers about this, in particular Sean Andrews, and I guess I'm interested to see if at even higher resolution, those rings turns into spirals for that one disk. The other disk, I wouldn't necessarily expect them to have these morphological shapes. Something that I've been a little bit interested in is what could be, so in terms of, in addition to temperature, something else that comes in these calculations is age, which is our linear dependence on gas masses in this model. And so you can imagine that there's a limit on how old a system could be if you believe this model and still be valid without being totally gravitationally unstable. I said that kind of weirdly. So if we don't see like large spiral arms, weird gravitationally unstable morphology, then and dust lines are correct, then we would expect that a disk could only be like for TW Hydra here, like after 10 million years, then you get a Q of 0.8, and then you could no longer expect this to be consistent.
All right. Ninka.
Yes, right. I have another question, which is how much do your results depend on the assumed age of the system? If you're using
it's a linear
dependence. Sorry?
Yeah, it's a linear dependence.
Okay.
Yeah. So if the disks were twice as old, then you'd get twice as massive disk.
Okay, that's not too bad. I mean,
yeah,
any estimates are within factor of a few, so that is fine. Yeah. Okay, great.
It's not so bad, but it is one of the uncertainties in this model for sure.
What about the turbulence?
Turbulence comes in. So that comes in it comes in strongly for CO, but it comes in for this model only when we model the dust surface density. So otherwise we don't care about alpha. That's assuming that for drift we don't care about alpha. There's some minor assumptions in there, but I think that's pretty sound. So that's actually something that's really nice about this model, is that just the dust lines themselves don't care about alpha. When we bring in the dust, we do care about alpha. For here, when I cite these dust to gas ratios, that's assuming an alpha of 10 to the minus 3. But yeah, that's the key assumption there.
All right, we are just about out of time. So I would encourage everyone to unmute and thank Diana for a really wonderful talk. Thank you so much, Diana.
Thank you so much for having me and for all of your really awesome questions.
All right, see everyone next week.